and responsibility and was called to service in hostile circumstances in command positions with the expeditionary warfare community during the first Gulf War. He served with distinction leading a section of 15 sailors as a watch officer of a radar sonar surveillance central with the Mobile Inshore Undersea Warfare Unit 113. Between assignments, Pablo opted to pursue what seemed to come natural to him, an aeronautical engineering degree at the University of Oklahoma. Shortly after graduating, he joined Northrop Grumman Corporation as part of the Flight Controls Technology Group, and so began his professional career with significant, noteworthy contributions to several projects, including the Defense Advanced Research Projects Agency, DARPA, Global Hawk Aerial Refueling Demonstration, where he counseled program and leadership teams through independent review and assessment of the program at major program events. He also has worked on the DARPA Oblique Flying Wing Program, where he led the recovery and successful innovation of a first-of-its-kind flight control system. Additionally, the U.S. Air Force Research Lab's Long-Range Supersonic Strike Program, where he rectified the control and aero-servo-elastic issues of the never-before-attempted TELUS supersonic bomber concept. The DARPA Unmanned Combat Armed Rotorcraft, where he developed a first-of-its-kind robust control. Today, Pablo serves as the program manager for the X-47B Unmanned Combat Air System Carrier Demonstration at Northrop Grumman Aerospace Systems. He manages a team of over 150 engineers and leads them through a complex transition from a technology demonstration program to an operational risk reduction program. Pablo provided the vision and technical direction to lay out both near-term and range objectives and executed a comprehensive reorganization of the program staff to reduce costs while providing advancement opportunities. Beyond his professional career, Pablo is actively engaged in STEM activities involving aviation. He is committed to introducing youth to the exciting world of aviation through the Experimental Aircraft Association's Young Eagles program, and is also providing in engineering cohort programs, which provide mentorship and guidance to students in pursuit of engineering education and an outreach program with local schools. Pablo's accomplishments have been recognized with Northrop Grumman's Most Distinguished Chairman's Award for Excellence and HENAC Luminary Award for Great Minds in STEM and other awards. In addition to a bachelor's degree in aeronautical engineering, he has also completed the Avionics certificate program at the University of California and graduate studies in control theory at Columbia University. Pablo's passion for flying began at the age of 13. He has since earned his commercial pilot's certificate. I now invite him to the podium to speak on development and testing of the X-47B. Mr. Gonzalez.
Thank you. It is quite a privilege and an honor to be here. Being the program manager of the X-47B is kind of a unique and rewarding experience in my career. I've never had a greater opportunity to work with some of the greatest minds I've ever had got the privilege of working with. They're an extraordinary group of folks. I am the program manager. I get to be the figurehead and come to these great events and talk about the program, but it is truly a very large team effort that got us here and got the program done. But before I talk about the 47B, I do want to point out that back in, I believe it was the spring of 1995, I was here in Dallas at an AIAA conference as a part of a student competition for a historical paper that I wrote with regards to the use of the Sopwith Pup as the first carrier aircraft. And I did not win that competition, so I'm very glad that now, 20 years later, I can redeem myself a little bit. But on to the X-47B. The aircraft is fairly unique in terms of what she looks like, and to really talk about what the aircraft looks like and why the accomplishments of it are so important. You really have to go back to what the whole point of the program was. Back in 2007, there was a pretty clear vision of what was needed in terms of power projection from aircraft carriers that really guided what the aircraft was. The first and foremost was that we're talking about a situation in which you have these short warning, aggression, access constraints. The world is still a dangerous place. It was back then, it still is today. And you really start looking at our forward-facing concepts. What the Navy brings to the table is really being able to put an aircraft carrier somewhere and support operations. But as you start looking at what that environment looks like, the range at which carriers are operating from threat areas is continued to get farther and farther and farther. And so right out of the gate, you really start looking at, you needed a platform that could do long range, just, organic, unrefueled range in order to really be able to stand the carrier off from these threats. And then you start looking at the large number and diversity of the threats out there and the number of missions and things you have to do. You really start driving you towards, you needed persistence. You got to stay in the target area for an extended period of time, which really drove this idea that you got to have to be able to refuel them, and you need a deep weapons magazine in order to be able to accomplish these missions, because you've got to put her out there for a long period of time. You really start looking at what was needed. You needed about a 1,500-mile standoff of the carriers from the threat, letting you put your tankers 500 miles from the threat. And you start laying all of that out and designing a vehicle for it and the threat environment. And you ended up with something that really needed a couple of attributes, the first of which was reasonable endurance. Second, had to be refuelable. Third, you had to have armament and an ISR capability. Laying that all out, fitting it in the constraints of the geometric constraints of putting it on an aircraft carrier, we ended up with the vehicle that you've all seen out there today. In terms of mission areas, right, and this was really kind of driving, those were the primary attributes, but then you had to have mission capabilities to do all these other things, going out, finding targets, doing surveillance strike. Those are kind of the basic bread and butter. Deep strategic strikes, interventions, and then being able to support special operating forces, manhunting, supporting those kind of activities. All those things are driving the requirements of what the vehicle needed to be. We really kind of captured it all under this idea of multi-mission persistence from a distance. It really was what drives the effectiveness of a carrier in the future, right? If manned aircraft and the range limitations that they have today, the persistence limitations that they have from having a man in the cockpit, really limit what you can do with an aircraft carrier, especially as those standoff distances keep growing. So it was all about global regional responsiveness, having combat power sustainability. That's really what was driving this idea of a deep magazine and being able to refuel. Manned aircraft survivability, the carrier survivability. This is all kind of setting the stage for how far away can you operate. And then lethality, right, is a question that continues to come up. It's something that's still being argued with respect to the U-class requirements. And so I guess I should take a step back. The airplane was designed based on what was needed in 2007. Those things are being argued today as to what's in the future, but the vehicle that is out there demonstrating now was about, right, lethal persistence and being out there. In terms of the program started in earnest. The contract was signed in 2007. However, it's important to note that the X-47B started its design cycle as a part of the JUCAS program that preceded the Navy effort that was put under contract in 2007. So the vehicles started to be designed, and some early production was done between 2004 2007. The UCAS-D demonstration contract was signed in 2007. Engineering changes were made to meet the requirements of that contract. And then between 2007 and 2011, we completed the engineering and build of the airplane. First flight was in February 4th of 2011. That was, like most aircraft, a very basic first flight, take off, fly around, come back. March 1st, we started doing envelope expansion, and that proceeded through September 30th. When we got to September 30th, we started working what we call the cruise configuration, starting picking up, cleaning up the gear, expanding the altitude envelope, expanding the speed envelope. And by November 17th, we had finished all the envelope expansion of the aircraft at PAX. During that time, we completed the second air vehicle. She came online, and she completed her first flight in late November of 2011. Moving on to 2012, we started working on some of the capabilities that were going to be needed at the carrier. May 13th was the first time that we'd done touch and goes with a UAV. We have not been able to confirm whether that's the first time that it's ever been done with a UAV, but certainly that was the first time Northrop ever did touch and goes with a UAV there at Edwards Air Force Base. Late in November of 2011, Air Vehicle 1 was packed up and trucked across the country. She arrived at the Naval Air Station, Patuxent River. As soon as she arrived, the second air vehicle was transported over. And then between September through November of 2012, did a lot of shore-based work, verifying the systems, verifying the connections in terms of telemetry of the aircraft to the ground stations and all of that at Patuxent River. And then in November, we started working the shore base cats and traps of the two air vehicles there at the facility at Naval Air Station, Patuxent River, where the vehicles are today, as a matter of fact. December of 2012, we craned one of the air vehicles on board the Truman and validated the ground control concept with the what we call the CDU, the control display unit, that allows an operator on the deck to move the vehicle around. Probably the least known, probably most important aspect, one of the most important aspects of dealing with the UAV off of the carrier was not really that whole launch and recovery, but how to get it into the catapult, how to get it out of the wires after she landed. That was all done with a set of technologies through the CDU. That was all validated there late in 2012. Then moving into 2013, started validating the precision GPS concept against the land-based runway there at PAX. A lot of surrogate work had preceded that, both at onshore and at the ship, using both a King Air as a surrogate for this 47B, and then at sea using an F-18 as a surrogate for the vehicle to validate that system. Before that was all pulled together, and then in May of 2013, we went to, did our first at-sea deployment of the system. A lot of work, we craned her on, did a lot of work, again, on the deck handling, working all the bugs out of that, and then did our first catapult at sea off of the George Bush with Air Vehicle 1. Came back, there was a short period of time there after AV1 catted off, and then we trapped AV2 a couple days later on the George Bush again. That was touch and go. I'm sorry, it wasn't really a trap. It was a touch and go. Those couple of days later, came back home. Had about a month worth of work to do a couple of tweaks and mods here and there. And then July 10th was the big event for us in trapping the airplane on the Bush. That should have been the end of my story right there. The program was slated to be completed by September of 2013. We did the trap in July. Those that have ever watched or were present for the press conferences, the program manager and the PEO, UNW, got up to the podium, did their spiel, talked about the program being over, and then the Secretary of the Navy got up to the podium and started talking about it's not over for the airplanes. That threw us a little bit of a curveball there. So shortly after that, we all sat down, worked out an extension to the program, including going back to going to the Theodore Roosevelt in November of 2013, where we did a whole lot of touch and goes and cats and traps off of the ship to validate and collect data to build a model of the burble, the infamous burble off of the ship. Completed that body of activity and then proceeded on to developing the next build, in which was really all about going and validating that you can operate these air vehicles jointly with manned aircraft. Up until that point, it was a very contrived, probably a bad word, but it was a test, right? So very defined limits. Everything was done very slowly. Exclusive use of the deck by the 47B. Took on the challenge of saying, okay, now we're going to go and deal with operating these things with everybody else. And started working on all the little bits and pieces of removing those limitations. And so in August of 2014, took the aircraft back out to the Roosevelt, spent 20 days on board, and we did a bunch of launch and recoveries in what we called cooperative launches and recoveries with the F-18s, and demonstrated that we could get her taken off the deck in 90 seconds and get her out of the wires and out of the way within 90 seconds to let the next guy land. And then the big decision in September of 2014 to take on aerial refueling. We completed the aerial refueling demonstration there on April 22nd, demonstrating the first time an unmanned vehicle has taken on fuel. There's a lot of words for one chart. So, the air vehicle itself, if you ever get a chance to look at her, she's a little bit larger than an F-18. She's 62 feet wingspan, not quite as long, but overall length is 38 feet. She is a truly LO relevant platform. The two demonstrators that are out there do not have all of the treatments for a low observable vehicle. So she in her current state, they are not stealth airplanes. However, they have all the right shapes so that you can put those treatments onto her. In terms of gross weight, she was designed for a 44,000 pounds aircraft with 2 weapons bays, carry 4,500 pounds of ordnance. Air Vehicle 2 is actually a little bit different from Air Vehicle 1 in that Air Vehicle 2, during her original build, we had done the work and made a decision to provision her to be able to do aerial refueling. So Air Vehicle 2 has a slightly different configuration of fuel tanks. She has additional plumbing to support. She had the additional plumbing to support the installation of a refueling receptacle and also a refueling probe. Ultimately, when we made the decision late in 2013, for cost reasons and schedule reasons, we decided only to install the fixed refueling probe and demonstrate the Navy style of probe and drogue refueling of the vehicle. That's considered the more challenging of the two. It was certainly more relevant to the Navy to go and demonstrate that. So we put that, that was Air Vehicle 2 now has a fixed probe. Air Vehicle 1 is still in her original configuration without a probe or without the refueling receptacle. She will carry 15,000 pounds of fuel and it has an endurance of 6+ hours. Now with refueling, we haven't really ever attempted to demonstrate that yet, but I'm hoping people will see the light and let us go and do that. In terms of spot factor, which is really kind of a single metric of how well you can stack them in the hangar deck, a spot factor of 1.0 is a F-18C. It's kind of the standard unit of measure, right? How many F-18Cs you can put in there. So she's about 13% smaller than an F-18C when you actually fold up her wings, and very efficient stacking, putting her nose to nose when you put them in the hangar deck. Talked about what allows you to go and do these the carrier landing. The big technology there is the precision GPS. For those that aren't aware, precision GPS uses a differential GPS that is augmented with very high rate, high accuracy inertial data that is shared over a data link to give you very precise centimeter accuracy relative position between the two bodies. And so that is the technology that's used to get them aboard ship. It is a very robust accuracy in terms of GPS for landing. A lot of software that went into the aircraft in terms of making her fly the pattern, behave like a manned aircraft. And really is about reliability and integrity for the manned aircraft, or I'm sorry, for the unmanned aircraft. We did implement redundancy for those systems with the IP-based TT&T network, and then the whole computing chain in terms of flight controls, the precision navigation, and the inertial data is all triple redundant. All of that combines with the G&C of the air vehicle to give extraordinary landing accuracy. We had a lot of requirements to go out and validate via modeling and simulation. All of that was done in what we call Sea State 5, 10 to 12 foot seas, the deck pitching up 10 feet, and a significant amount of yawing motion of the carrier deck. When you put that all together with the PGPS, the TT&T data link, and the aircraft at minimum fuel to trap, and really that was about making the air vehicle as responsive to disturbances as we could expect. You put all that together, it's a pretty severe environment that you're looking at. And if you look very carefully here, let's see if I can. So if you look, there's a couple of red X's there. That scatter of red X's there is representative of an enormous amount of landings. And you can see the scatter is predominantly in the longitudinal axis. A lot of that has to do with the pitch of the deck as it moves up and down at a 4.5 degree glide slope. That translates into a lot of fore and aft motion. The lateral motion you can see is within a foot. It was 1 standard deviation of lateral motion. In terms of where she touches down on the deck, I will tell you to date on the ship, we have never missed a wire. We've done over, I believe it's 16 traps at sea and have not missed the wire yet. The flight controls and the precision of the PGPS is extraordinary. A lot of questions in terms of the modeling conditions and how the ship motion was properly replicated. We did not do that in terms of a physics-based model. The ship motion was really driven by actually taking data from the ships. We instrumented a couple of ships, collected a bunch of data. That data was fed in to all the simulations in terms of their motion to make sure that what we got out of our modeling and simulation effort was true and representative and faithful to the real motion you see out at sea. But I think the most interesting part of the program went well beyond the technologies. Both aerial refueling and putting the aircraft on the deck of the carrier really forced you to bring an unmanned vehicle, a 22-ton unmanned vehicle within feet and inches of human operators, folks on the deck, and the tanker itself, right? Ultimately, you come into contact with it. That was an enormous challenge in terms of building trust with the human operators that are out there with this vehicle. The entire test program went very, very rapidly. And I will tell you that the speed at which we were able to go, there was 2 limiting factors, right? Number 1 was how well did the flight performance of the vehicle match with modeling and simulation. And in the vast majority of cases, that was extremely well matched. The other limitation was how quickly was the test team and the folks involved with the vehicle comfortable with moving on to the next step. That ended up in many cases being the limiting factor, right, in terms of the pace of the program and moving forward. So there's a lot of challenges with bringing the technology to a community that is inherently conservative because of the level of dangers that they face out there with manned aircraft. But as I talked about in July of 2013, seeing was believing. You had to get out there and actually do it, prove it, demonstrate it. And like I said, knock on wood, to date we have yet to miss a wire and catch on board the ship. The big element for me personally, was aerial refueling. I started working aerial refueling in 1999 as a part of the original Air Force UCAV program. It was always, like I talked about in the requirements, based on the mission, it was kind of an acknowledged thing that it really needed to be there. The program was not willing to take that on with the original contract in 2007, quite simply because of the risk, right? But we continued to work that in parallel with all the work on the ship, really to address, like I said, the QDR 2006, which was, like I said, based all on operational analysis of what was needed to keep the carriers relevant. Pull that out, that was a true requirement that was needed for those vehicles. The technology set for autonomous aerial refueling leverages heavily on the PGPS that was developed for the carrier landing. The Navy did not do this alone. Northrop Grumman did not do this alone. Those of you that may think back and remember during the JUCAS program, AFRL had a autonomous aerial refueling research program, development program. Northrop Grumman was a part of that, as was Lockheed and Boeing, all together working on those things. The UCASD program picked up the work done there, expanded it, extended it to work the Navy problem in terms of probe and drogue refueling. And so we brought into that mix a vision-based navigation solution that combined imagery along with the inertial data and the GPS data to come up with the navigation solution to go do aerial refueling. The whole game plan, since right out of the gate, was to use surrogates. A lot of surrogates were used, but a whole lot of credit needs to be extended to Calspan Corporation. The variable stability Learjet was used by the Air Force program, was used by the Navy, was used by Lockheed, Boeing, Northrop, all to go develop and work these technologies under the safety of a surrogate that had a manned safety pilot before we transitioned it onto the UCASD. But this is the most common story referenced as the first refueling event in June of 1923. Was not actually the first. It was a very public event and spectacle. A lot of people reference it, but it was not the first. It's also the belief that the question mark, the flight of the question mark, which was a modified C-2A, it did set a record for staying aloft longer than anybody else had previous to that. But it was not the first to refuel. This one occurred in January of 1929, flight of over 150 hours. Again, the limitation there ended up being the engine and its ability to carry on under those conditions for 150 hours straight. She was crewed by a 5-man crew and commanded very notably by Major Carl Spatz. For those that don't recognize Major Spatz, you may recognize him as General Spatz, who later became the commander of Strategic Air Forces. He was the first commanding officer of SAC, and he was the guy who drove the U.S. effort to make aerial refueling a basic capability to be able to refuel bombers to support the strategic bombing missions in the Soviet threat. But the first real instance of aerial refueling was in 1921. 3 gentlemen, Wesley May, Frank Hawks, and Earl Dougherty, were the first to do an aerial refueling. They physically grabbed a 5-gallon tank, strapped it to the guy's back. He walked out on the wing, did a pull-up onto the other wing, moved over to the airplane, and put fuel in her. We regularly focused on this picture during our kind of quarterly team meetings, in that success requires a personal commitment. It was heavy on risk, light on automation, and I will tell you that even though we talk about as heavy on risk, if you ever get a chance to read the story on it, it's quite interesting. They did a lot of preparation for this flight, and in his memoirs, Mr. Dougherty talks of the fact that the one thing that they forgot to account for was the weight of the fuel. They had practiced doing the pull-ups and everything with an empty fuel can. They actually had to fill it up, and he almost was unable to pull himself up because of the extra 30 pounds on his back. In terms of what the system looks like, it really was about developing a system that mimicked what was going on with manned aircraft. So we have a set of requirements that were levied on what ended up being something that was somewhat roll-on, roll-off kind of capability for the tanker. Omega Air Refueling Services, which is a commercial refueling outfit that the Navy uses and provides a lot of support. We were put under contract to provide that. The Navy actually developed the tanker side of the equation to provide the PGPS and the inertial portions. And we actually have an operator station that was on the tanker that was able to command the vehicle. The vehicle itself, we call the receiver segment. The entire system was adaptable to doing boom receptacle and probe and drogue refueling. In fact, the software that was written that's on the aircraft has all the software in it to go and do boom receptacle refueling. It's just not turned on because it wasn't fully vetted and tested prior to going and flying. In terms of what the technical challenges were, obviously the navigation, again, relative navigation. We put in sensor systems that we say replicated the pilot's vision, but is a little more than that. The sensors we actually used were infrared sensors. That was driven by a lot of studies early on in terms of being able to reject noise in processing the images. It actually goes out, finds where's the tanker, where's the drogue, and then it uses that information along with the inertials and the GPS data to figure out where it is in terms of where they are on the Earth. The first challenge in aerial refueling is getting the two airplanes in close proximity to each other to start the precision formation flight. So you have to be able to get there, get close first to switch into this precision formation flight mode, where the control laws were really written to try and mimic and replicate how pilots do this mission, right? So it senses your relative position, relative orientation of the tanker, and then it actually stabilizes the aircraft and maneuvers to fix positions relative to the tanker. There was a clearly communications challenge in terms of doing this. The operator of the X-47B is on the ground. He is not necessarily in line of sight communications with the tanker. So there's a whole voice relay system that has to occur in order for the ground-based controller to talk through the aircraft to talk to the operators on the tanker. In terms of the technologies, like I talked about the vision system, it is an infrared-based imagery. TT&T provided the backbone of the communications between the tanker and the air vehicle. The flight control EGIs, they are GPS and inertial integrated navigators. The 47B and the tanker both used the Honeywell H764s, although I will, however, say we actually have done a lot of lab work and some testing with surrogates with the LN 251s units. The VMS, there's a vehicle management computer, a precision navigation computer, and a mission management computer that are all redundant on the air vehicle, along with all the algorithms that go into that. On the tanker side, there's again the embedded GPS inertial nav system. There was an engineering workstation that allowed them to monitor the health and welfare of all the systems that were on there. Again, the TT&T data link that provided the backbone of the IP-based communication between the two. There's this thing they call the SIP, System Interface Processor. This is the same box, the same computer was used on the ship to support carrier landings, and then the tanker operator station, which mimicked to a great extent the control capability of the mission control station on the ground, but then it had tanker unique functionality in order to initiate breakaways and things of that nature. And then the Omega tanker was upgraded to include a high-definition camera to be able to monitor the operation. Talked about at the beginning there the human aspect of this and trust, and we all pull that down based on integrity. PGPS, as it sits today, has not met the integrity requirement that was originally levied. From a test perspective, we're able to demonstrate and convince ourselves that it was safe enough to operate at the ship, but we were never able to verify and validate the original requirement of trying to hit a 10 to the minus 6 probability of integrity event. What we were able to do on the AAR side of the house, though, was the vision system brings in the same type of information in terms of relative navigation to the tanker, relative position and orientation as the PGPS does. But because they are subject to a very different set of faults, the common mode fault that resides on the PGPS side, regardless of how many GPSs you are carrying, does not reside on the vision side. The vision side has its own set of common mode faults, but they don't reside on the PGPS side. So when you put those all together, you get a level of integrity that is extraordinary in terms of being able to trust it. We were able to demonstrate drogue tracking and engagement with, like I said, the CalSpan variable stability Learjet from both a ground-based operator, and then on the surrogate test program, we actually used the control station on the tanker to maneuver the aircraft. And this is all done with a standard drogue. There was no modification to the drogue itself. And as I pointed out, April 22nd, extraordinary event in my career, extraordinary event for our team in terms of demonstrating aerial refueling with the X-47B. We had a requirement to make contact with the drogue at least 3 times. We were able to do 5. We had a requirement to stay in the refueling position for a minimum of 5 minutes. We stayed in the refueling position for 11 and a half minutes during this test. The objective was to transfer 3,000 pounds of gas. Post-flight, we validated that she took on 41,014 pounds of gas during that event. And I have to hand it all to a young lady who was our flight fuel systems engineer, who during the test wanted to make sure we got 3,000 and convinced him on the fly to stay in the slot just a little bit longer. So we ended up getting 4,000 instead of the 3,000 that we originally were after. I'm going to hold for questions. I believe we've got a video that we can play. How are we doing? Okay. Questions? What's next for the program? I will tell you that there's a lot of folks that would like to know that. There is a lot of debate and discussion within not only the NAVAIR organization in the Navy, but Department of Defense and in Congress over what the requirements should be for a next generation platform, and how does the 47B play into that discussion and debate. Where the program is today, we are currently in a mode of preserving options while decisions are being made. So my team right now is out. We keep the airplanes in a flight-ready state, running engines, doing all the maintenance. There are a number of options that have been put on the table in terms of things that the 47B could do, things that we probably should do, and things that would be nice to do. Those things are all on the table and range from doing validation work for JPALS, since JPALS is a program of record, but they are only committed to demonstrating the manned portion of JPAL. So the 47B, I think, is very well equipped to provide value not only to unmanned aviation for the carrier, but also for the JPALS program as they proceed to Milestone B. There's a whole body of work in terms of aerial refueling for the Air Force refueling that has not been addressed. And then when I talked about originally in 2007, the Navy produced a set of requirements that they were called the Carrier Relevancy Demonstration Requirements. Those requirements had a whole slew of things that the vehicle needed to be able to do that we were not put under contract to actually go do. So that whole array of capabilities is on the table. So we're waiting patiently with I think safe to say the rest of the industry that's looking at the U-class program, looking to see how that all shakes out and what exactly does the role of the X-47B play in that whole path forward. So a lot of opportunity there. Don't know how it's going to pan out. Anyone? One more?
Hi. I'm just wondering if you see any pathway for the amazing developments that are going on with the X-47, if there's any pathway for that to transfer to the civilian sector?
Say again?
Is there any pathway for the technological developments that are going on with the X-47 to filter through to the civilian sector?
So I think in terms of the commercial side of things, clearly there's a whole host of efforts with regards to unmanned vehicles participating in the commercial market. And there's a lot behind the 47B in terms of the level of autonomy and capability that's there that I think will play in the future of commercial UAVs. Now, there are a number of technologies that are there that are equally applicable to manned platforms, and I think actually will transition to the commercial side. The precision GPS technology, that level of accuracy in terms of supporting automated landing capability would be, I think, equally welcomed by manned pilots, be they flying fighters or cargo aircraft or passenger aircraft or whatever it may be, right? Knowing you are on the glide path within inches is just as applicable on that side of the fence as it is to landing on an aircraft carrier or anything else. I don't think that aerial refueling in and of itself is going to find its way to the commercial side of things. There's better ways to solve the range problem for commercial aviation than there are for military aviation, where you're balancing payload both in terms of fuel and weapons and all those other things. But certainly some of the technology, some of the work that was done for aerial refueling is being incorporated, and some of the lessons learned out of that have been transferred back and forth between the aerial refueling technologies and the sense and avoid technologies that are being worked. And so there's a lot of cooperation and going back and forth between those teams, at least at Northrop Grumman, and I believe that that's the case at AFRL as well. So applicability, maybe not direct, but certainly the lessons learned and some of the technologies coming out of that will migrate their way into the commercial sector as well. Thank you.
Great talk. Enjoyed that. Great work.
Appreciate it.
I'd like everybody to stick around and Pablo and congratulate him. Let's see if we can do this correctly. And our photographer's over here.
Thank you, everyone.